Hi, good morning. So actually, it's a great pleasure to see you all in person after the pandemics. And the driving force behind this workshop is, of course, Professor Lev Vaidman. So I'd like to thank him for, doing all the work with all the administrative staff. And typically, every conference has some goal. In our case, the goal is not mine, it's Lev's goal, is to convert you to MWI. But since we are scientists, we would like to check, at least classically, whether it's successful. So I would like to ask you just to raise the hand if you are now in favor of MWI as the right interpretation. Then we will ask you the same question at the end, and then we'll see the result. It will be, of course, not a very precise statement, but still. So who is actually in favor of? Okay, actually not the majority. Okay, good. So the success of the conference, as we will report to the funding agencies, will be whether the number is going to change. I don't know, Yakir is around? Okay, so I'd like to begin by actually congratulating Yakir for reaching 90. It's a non-trivial age, and Yakir is still working and publishing like a young postdoc, so he's really a great inspiration to all of us, and we will see him definitely around. So these days, actually, there is an interesting situation in science in the sense that the public is very interested in quantum mechanics. So if you see all the newspapers, everybody is trying to understand what does it mean that the beat can be 0 at 1 at the same time, etc. And many people are talking about it, and that reminds me a little bit of this when Stephen Hawking wrote his book, The Brief History of Time, everybody bought that book, but nobody knew exactly what's written there. So it's the same situation now in quantum physics, but to be fair to the public, actually we are also confused. In fact, the Nobel Prize of Physics this year was about entanglement, which is still weird to probably most of us. But now governments and also, of course, funding agencies of all kinds and companies are investing a lot of money in this field. And it's actually pretty difficult to really give a broad view of what's happening there. But if we just look at the field of quantum computing, interesting things are happening there already. In the sense that we already have some, what we call NISQ quantum computers, the noisy ones, where you have all kinds of qubits connected, but there is no error correcting code. And actually the goal of most of these companies is like in 2030 to have a large fault-tolerant 1,000 logical qubits computer. And that's interesting because the question is, what can you do with it? And it turns out on the theory, if you will look at quantum pH every day in the archive, you will see zillions of papers. But in fact, the progress is statement of a new mathematical playground. So you have superposition, you have entanglement, you have no cloning. And let's play with these rules and ask what happens. But when they come to measurement, you will notice that only in their books there is only one thing. It's called collapse. They have no idea that there is something else. They don't think that there is a problem. And I wonder at which point this will become an issue. Before the pandemics, we established the Center for Quantum Science and Technology. And in fact, we had what see that the name of the center is written on that pen so that you will not forget us. But second, you also got a T-shirt. And I was asked by someone in the board of trustees of the university, these are people from the public sector who supervise universities, So he asked me, what is a physics Olympiad? So I told him, oh, it's very simple. They are solving physics in problem while running. So that will be the good thing for you. True story. That will be a good thing for you. So the center that we established has several dozens of labs, and we are interested in all kinds of topics: quantum computing, communication, quantum materials, sensing, etc. And we have already established interesting connections, important connections with other institutions around the world. Now I know that all the places that you come from probably have their own center, and so it would be nice if you connect with us. It could be all kinds of things. Could be joint research. It could be joint PhDs or postdocs, etc. You can either contact our scientific administrator, Ronit, or Lev, or me. I think it's important for this ecosystem to function well. So let me stop here, and I'll give the place to Rabbi Lev, who is going to convert you to MWI, and let's have fun. Thank you.
Thank you, Yaron, for opening the conference, but may I mention something which may be a little controversial too. The whole kind of big hype and all happened because of quantum computer. And I believe that the father of quantum computer really David Deutsch. And David Deutsch believed in many worlds. So without many worlds, there will be no quantum computer. So essentially, yes. So at least, yeah, okay. Maybe it's too high. Okay. So I think many world is responsible for all this big industry, but it's not accepted. And for a long time, I thought it should be accepted, and I want to bring it to consensus. Oh, maybe I will be less happy, but if during this week people explain to me that it really doesn't work, I really want to understand. So for me now there is a big misunderstanding why many world is not in a consensus. Because I have an entry in Stanford Encyclopedia, and I say that this is essentially the only interpretation which has no action at a distance and which is deterministic, which I believe a great property and needed for theories, and what I believe scientists at least 150 years ago was trying to, at least 100 years ago, looking for something like this. Then came quantum mechanics with uncertainty relations, and people saw that we need randomness, and then it was EPR, and people said we have to accept non-locality, and last month's Nobel Prize I think everyone knows that nature is non-local. And and maybe main interpretation of this non-locality is that there is an action, maybe spooky action at a distance. And I don't feel comfortable with this. And for me, this conference is really to see, can we have good description of nature without action at a distance? So why many world is not in a consensus? There are a few people who, maybe not, unfortunately, not so few, who wanted to come, and I invited them, and they couldn't come because of different reasons. And I sent them this question, why many world is not in consensus? I start getting some answers. I will give some here. I have my answer, and this is my answer. How it's an answer to this question? You see, more than 2,000 years ago, there was an idea that Earth really not in the center of the world. And much later, then Copernicus kind of put it in a scientific grounds. I think about 100 years later, people were prosecuted trying to promote this theory. And only maybe 200 years ago, people kind of accepted that this is the right thing. What Copernicus did, he removed Earth from the center of the universe. humans want to be a center, and our planet is supposed to be a center, but he showed that it's not. And whatever he did, something very similar. He removed Earth from the center of our world. There is a big universe, and he said that there are many worlds, and our world is not the central one. And people, it's hard to accept. I think now things develop much faster, so I don't think we'll have to wait so long. So it will be accepted. Oh, maybe you'll show me that I'm wrong. So the many world is not in the consensus yet. In fact, as I said, a long time ago, I believed that many words is the best interpretation. My first paper on many words, which kind of showed that people didn't like many words. It was rejected, I think, more times than any other paper. Although finally, it had a pretty nice number of citations, and some editors said that they mistake not publishing it. But this shows that when I first wrote it, it's more than 30 years ago, and I said I consider many word interpretation the best available quantum theory. But some of the responses I got now, Chris Fuchs told me or wrote to me, its main shortcoming is simply this: the interpretation is completely contentless. The interpretation actually does not say anything whatsoever about reality. And I got more responses of this kind of maybe more serious. And Jeffrey Barrett, who had a parallel entry to Stanford Encyclopedia on Everett, he said it does not explain why one should expect to have that particular experience in the world described by the theory. So this is kind of a hint, and maybe this will be a conclusion. People want from a theory something which I don't think it's supposed to provide. This is the theory. The theory, the many words says that there is one big universal wave function. And it has no collapse, and it evolved according to nice equation, well understood, very tested by more than 10 digits in experiments. And it has this nice picture, which I think you have on your t-shirts. But in fact, I admit that there is a serious problem. If God will give you the wave function of the universe, it will be very hard to find our world there. This is, and I think many people ask from many word interpretation, give me the whole ontology, which is the universal wave function, and show me the world we are here. What this ontology tells us, it's ontology of many words. It's a proposition of different words. In fact, the words are kind of, at least I defined it in reasonable layman terms. Every classical object, every macroscopic object should be well localized. And then I can kind of write a wave function of the world in which there is a product state of all macroscopic objects in their macroscopic variables. They have some internal variables which have some entanglement which we need to explain superconductivity, stability of atoms, and everything else. But macroscopic objects themselves are product state, and they live in three-dimensional space. So we have this macroscopic objects in three-dimensional space, and we have some constituents of this which are entangled themselves and live in three-dimensional space, and a number of constituents. But it's very big project, and it's not clear how easy it's possible. Maybe it's really the initial state of the universe very important that there is success for this. It's not clear how to, out of the wave function to get this. And it's much easier, and this is what I think is needed. Look on our world. Our world has this structure as before, as every world. Our world has all these macroscopic objects. Every macroscopic object lives in three dimensions. It has some internal microscopic particles which are entangled. But the objects themselves live in three dimensions. So every textbook kind of very happy when they have collapsed, the collapsed word on textbook, it's one of the many words. And most people see no difficulty to recognize what we see around from this collapsed world, collapsed wave function. And the collapsed wave function is our world. Our experience related only to these macroscopic variables of macroscopic objects in 3 dimensions, like in classical physics. It is hard to see the emergent branching structure in something like this, but when we have just one, it's easy. And it seems to me that I look for science, and science tells me it should explain, science aims to explain and understand science as a collective institution, more accurate natural explanation of how the natural world works. And it seems that many people don't want this, they want more. They ask how the world is. I think this is difficult, but we don't need it. How it works, it's enough. What does it mean, how it works? That if we know particular situation like preparation of experiment, we know to calculate the outcomes. Also the experiment, this is maybe the experiment. And we know what will happen. We observe it, it's correct. In quantum mechanics, it's also correct. But in quantum mechanics, it's a little more complicated because there are 2 kinds of experiments. In classical, we have all deterministic. I know what will happen definitely when I leave it. In quantum mechanics, sometimes we have deterministic experiment and sometimes we have probabilistic. They are more complicated. But I believe with many words we can explain both, and I believe that many words is the only theory which has this no action at a distance, which I think very hard for me to accept. This is why I go to many philosophy conferences trying to get support from them that this is bad. I don't. Maybe here, and I think this is what when people should discuss. How bad is the action at a distance? Randomness, I think, also pretty bad. So, one thing which I also was not able to persuade to everything, but I will try on one foot to say why I believe that the many world is the only theory which allows, which removes action at a distance. Because never mind which interpretation you take, even you don't take, even if you give up and you are cubist or whatever, if in the following situation, simple situation, there is an action at a distance. If I have a EPR pair in a large distance, here I put one EPR, one particle here and another particle on the moon. So if I don't touch this particle, I have on the moon unpolarized electron. If I measure it, I immediately make it polarized. And for me, it's a real change. So I can maybe demonstrate by constructing a game. There is a game. In particular moment, known to us, there will be measurement of the other spin on the moon. And if it will be up, you'll get $, and if it will be down, you'll get nothing. So I think everyone now is supposed to be ready to pay a game. You give me 10 cents and you play the game. If it's up, you get $1. And again, the bet may be everywhere. In fact, maybe here or maybe other place. But it's about the property on the moon, because the experiment will be on the moon. So it's clearly describes something on the moon. And the point is that everyone is ready to play, but when we have this situation, when we have a pure EPR, now it's ready, but in the moment I measure, no one will be ready to play against me. If I'm here, measure it. Far away, there is 1 second of flight to go to moon. And, but no one will be ready because I know the outcome. So it's clearly something changed there. Unpolarized became polarized. Now, measurement on Earth make immediate change on the moon, and polarized spin become polarized. So, what's about many words? Many words doesn't say anything different. If a place is this kind of game, also if I believe in many words, everyone is ready to play with me, and at the moment I performed a measurement, No one is ready to play with me. So it looks like there is an immediate change. Yes, the immediate change happened in every word. But physics is not for every word. Physics describes everything. If you look on all words together, then the spin on the moon, it's still unpolarized. In every word, it is polarized. So there is non-locality, there is this entanglement, non-separability. There is non-local connection between the different parts. But it is, if it is within our word. Word is non-local concept, and but the physical universe and physics describe the whole universe, all words together. Nothing happened because the mixture of up and down and the EPR, one particle of EPR pair is identical from local point of view. As I said, the quantum physics and even without word, the single word explain very well if we have experiment with definite outcome. This experiment with different outcome, and here another experiment with definite outcome with classical physics cannot explain. We have a Mach-Zehnder interferometer tuned in such a way that it always goes to one place. So classical physics cannot explain it. Quantum physics explain it well. We have, he says particles are waves, and so when we send particle, it splits and then make interference, destructive interference in one place and constructive in another place. And we have full understanding of this kind of experiment, which classically we couldn't. The difficulty with single word physics is this experiment, much simpler one. Just a beam splitter and two detectors. Because this is what tells us quantum physics. Quantum physics tells us that both detectors change, their quantum description changes. And when we look on them, we can look some maybe photomultiplier to understand a little more. And still, quantum mechanics tell us both photomultipliers should evolve together. This is a pure quantum mechanics. But what we see just maybe one, or sometimes we see another. We never see two. If there is a one word, we see we cannot have this situation. In one word, we cannot have that both photomultiplier click. The many word solves it. Now, there is other issue, which I think was a main obstacle for believing in many words. This is our word, and when we perform quantum experiment, then the words split. And there is a very natural question when you perform non-deterministic experiment. You want to ask, what is the probability of an outcome? So, in many words, you cannot ask this question. And this is very unusual. People, in the moment you accept many words, you should say, no, I cannot ask the question, what is the probability for an outcome? Very simple, because all outcomes happened. So there is no probability for A or B, because both A and B and C, all outcomes happened. So there is a problem with the meaning of probability. If I have this simple experiment, we send, there is no meaning for probability before the experiment. You send a photon or whatever, and there are two detectors, and there are non-zero probability. So quantum mechanics get us both. And if I really believe in quantum mechanics fully, in many words, then the observer or splitter will look on both. And you cannot ask what is the probability. We'll have one observer seeing A and another observer seeing B. Now I can maybe try to play with it. Maybe I look after the experiment in a single word, I see, if I single word per person, I see one outcome. Can I ask what is the probability? And even I even believe, I think in the word B, he sees B, but the probability in word B to see B is 1 and to see A is 0. I want quantum probability, which I see in experiments. And I don't get them. I may trick these other things. I think Sebens and Carroll was trying to do this kind of idea. Let's put a wall and perform experiment when the observer is behind the wall. So experiment finished, there are two words, there is word A, there is word B, and ask, in which word am I? I say, this is also illegitimate question. You cannot ask in which word the observer is because he is in both words. So, in fact, I believe essentially it's this paper, which took like 10 years to be published, where I think I have a solution for this probability issue. You see, before the experiment, you cannot ask the question, what is the probability of A and B? If you perform the experiment and the observer see it and get the experiment, you also cannot have meaningful probability. If you observe the experiment and you do not split, but you're far away and nothing happened to you, you also cannot do anything. And my solution was, what you have to do, you have to go to sleep, and during the experiment, you moved. And then when you are awake in identical rooms, only you have a meaning of probability because you do not know in which word you are. And now there is a matter of fact. Everyone in A and B, and he doesn't know. So then if you replace probability by self-location, this I believe is a solution. So ignorance about self-location replaces ignorance about outcome of a measurement, which you cannot ask what is the probability for outcome of a measurement. And so then you put kind of a Born rule, which I think you cannot really do. You have many reasons why the Born rule is correct, but you have to postulate some of it necessarily, which correspond to this measure, what is amplitude square in every place, and you need this postulate. The probability of self-location is proportional to the measure of existence. Now, and I want to essentially end my talk and start the conference with a really experiment. Let's split the board. You can go to my homepage. You can do it every time when you have difficulty to make decision. And so let's say you can define two words. Two is good. You put foo, it will be 4. Let's put 2. And let's put left. Sorry. And this is right. And there is an interface that is connected to some quantum device which will perform experiment. And now I put split. And I got right. It means that now, if I got left, I will move left. If it got right, I go right. So I start with the right, get off on the right foot. I believe this word is great. The only problem that I'm a believer in many word interpretation. I'm sorry for my parallel word in which it started with the left foot. So, but this is physics. This is what it is. Thank you. I think we have many, maybe one more issue, the practical issue. I don't think you need. I don't think there should be questions now, especially because of the bus we started late. But in general, I will just repeat. The idea to give presentation for 2/3 of the time and to make discussion. Philosophers are very used to it. They maybe even half of the time discuss. Physicists used less. Because I want discussion. This is what there is any chance to get a consensus. All technical, it doesn't mean how many technical details you bring. So I will stop here, but please, for all talks, don't finish your time. Leave time for discussion.